everybody. I am Muhammad Yusuf, field geophysicist. Today, I'm gonna present the unconstrained blended seismic data acquisition for ultra-dense exploration. Today's talk, we will speak about the technology highlights, Western Desert subsurface imaging, achieved projects in Egypt using our new technology, data flow and the quality control, examples of the deep blending results and seismic comparison, and conclusion. Affordable density, single vibrator per VP. In the conventional acquisition, we were using a fleet composing of 3 or 4 vibrators. With the new technology, using the same model of vibrator, the same number of drivers, we have put the acquisition to be more denser by putting a single vibrator per VP and decreasing the shot point interval. Applying these factors, we have increased the VP rate per hours, we have increased the VP density per square kilometer, and we have reduced the turnaround. Motivation. Our motivation is to improve the productivity of seismic acquisition for the same quality or improve the quality densification for the same.
Seismic acquisition for the same quality, improve the quality densification for the same. In which way we can do that? We have put the source arrays at molecules. Now we are using a single vibrator number to see very high productivity acquisition blending shooting. So we are shooting during the listening time. There's no time constraints anymore. Every vibrator is shooting once it's ready. Unconstrained vibrator, so no waiting time, no step time. We are not waiting anymore for step time. And the continuous recording. This picture is a seismic record composed of different shot points at different locations from different vibrators. The challenge after is to blend this shot point to a normal way of acquisition. So we have put back this shot point here, like the conventional acquisition. So efficient source separation solution to recover blended data and a huge amount of data to store. This is an acquisition sketch showing the green line or the receiver position in the slash, and this the black dots are the spread, and this are the vibrators. So each vibrator, as you can see here, they are sparse shooting as random as possible in both time and space. And this is the batch of receivers that needed in order to move to the next side, the next source file. Broadband sweep, the emphasized sweep. Emphasized sweeps are designed to fill the maximum available bandwidth within the limits by varying the force and the sweep rate with frequency. As you can see from this picture, this curve is the linear speed from 5 to 80 Hz, and the green curve are actually the emphasized speed, the broadband speed from 1 to 80 Hz. So we have both, and here are the mechanical limits of the vibrator. And as we can see from the picture, we have added more signal energy at low frequencies, slow, well timed despite mass displacement and flow constraints. So more time spent on generating low frequencies without reducing the energy in the regular range of frequency. There's another challenge now called the clean sweep. Clean sweep, as we can see from here, this is a DVSA, or the time varying spectrum analysis of the broadband sweep. This is the pilot signal that we aim to put to the ground. And here are the harmonic noise. And these noise actually are generated by either the vibrators or the ground. It comes up from the coupling between the base plate of the vibrator and the earth. So the harmonics generated by the vibrator with the broadband sweep, using our new technology, clean sweep, this kind of noise disappeared here at low frequency, leading to better imaging to the deeper darkness. The effect of custom sweep seismic data. So as we can see from here,
this is the effect of custom sweep on seismic data. This is one shot point using the broadband sweep, and this is the same shot point using the broadband sweep with our clean sweep. This is the ground roll, the first break, reflections, and as you can see from here, this is a harmonic noise, self-contamination. So this noise actually are generated from the same vibrator producing the shot point. And this noise is a contamination by harmonics generated by the next VP. Using our new clean sweep, this harmonic noise disappeared. Western Desert subsurface imaging. So the challenge in the Western Desert subsurface imaging is the imaging of sections below 2 seconds. This is a vintage final pre-stack depth migration full processed using conventional acquisition, while this stack is a raw field post-stack time migration image from de-blended output. This is the same subline as this. This is the old technology, conventional acquisition, and this is the blended acquisition. This stack is generated using only one velocity low. There is no any velocity picking done on this, and this is full process. You can see how the resolution is getting better in deeper target. We are below 2 seconds. So this technique gives you better imaging to deeper targets. Unconstrained blended seismic data acquisition unlocked the stratigraphic details and improved the fault resolution. Yani check it out 2018. Unconstrained blended seismic data acquisition in Egypt. So this acquisition acquires high subsurface resolution with 1/4 less time of the conventional acquisition. So we give better data with less cost and less time. Since the last quarter of 2017, Argas, a subsidiary of the Arabian Geophysical and Surveying Company, has conducted 4 3D seismic survey using this new technology in Egypt Western Desert. Here are the boundaries or the area of interest where we have done all our 4 projects. So we have done 2 projects for Apache, 1 for Khalda, and the last one we have acquired was for Shell 2 weeks ago. And here this table shows the surface in square kilometer for all the 4 projects we have done in this area. And the third one was a bit bigger, where it exceeds 4,000 square kilometers. In this third survey, we have found 6,200 of non-seismic objects like oil wells, quarries, pipelines, water wells, etc., and farms. And in this survey as well, we have found more than 16,431 discovered unexploded ordnances. This is a remnant of a rocket body from the World War II. This is the unconstrained blended seismic data acquisition parameters that we used for our clients, for Apache, Khalda, and Shell. So we have actually the receiver point spacing and source point spacing were 12.5 meters, and here was variable in this case, and both of them have used our broadband clean sweep. This actually is 5 days of real unconstrained blended acquisitions. You can see from this movie, all these circles actually are the vibrator, and they are shooting everywhere in different time and different positions. Each one of them are source lines, and the green lines are the acquired VPs within 5 days of real production. General view on data flow and the QC. Okay. In the recorder is having a continuous seismic record each sample of time, and this seismic data is dumped on NAS disk 3 terabytes per day. And there is a correlation of this data is being done for QC, for real-time QC purposes in the seismic recorder. After that, this data is being transferred to the in-field QC geophysicist trailer in the field, so that he can run his own flow to make sure that the data has been acquired in accordance with the client specifications, and to send the bad VPs to the observer for reshoot. We can see from here the SIGD data came to the QC office for data correlation. So we are correlating this non-correlated SIGD data with the pilot suite. We will have seismic displays, and then we are merging information from the SIGD with the ground forces and with the auxiliary files to have clean SPS. In the second step, we have SPS pre-check software aims to remove the duplicated VPs and to know which VP was good, which VP was bad, so that the bad VP is being reshot the second day. At the end, we will have data chunking in individual records, so we chunk the data so that we can have a conventional overview to the shots, and we will have a TeraMake. TeraMake is a software which is producing in-field fast-track pre-stack time migration in real time. Once we QC the data in the field, we send both raw SIGD data and SPS files plus auxiliary files to the processing center. The processing center is doing its normal reformatting, producing RMS maps, doing the deblending, which is putting this continuous record to the conventional way of acquisition, and then producing some cross spread, stacks, and RMS maps, and then we convert this data after deblending to SIGY, producing the SPS, compare both of them, and send the data to client. This is an example to the in-field fast-track TeraMake pre-stack time migration. The input of this are the blended data. The input of this are the raw data from the field. This is done by using only one velocity function in the field. This picture is an example of blended shot points. They are 4 receiver lines, 16 kilometers each one of them. And as you can see from here, there are different shots in the same receiver at different time. For example, this can be the apex of one shot point. This is the apex of another one. This is one more shot point. This is the same shot point after the blending. So, blended shot points, de-blended shot points. Blended shot points, de-blended shot points. So we have removed all the other vibe interference. This has disappeared, the other one was disappeared. This is the de-blending example, where we have one receiver line here with blended shot points. This is the same line after de-blending. And these are the differences. So the other vibe interferences. Example 2, blended shot points, data after the blending, the same receiver line. So we have removed all these interference from different types, and we just kept our main shot point. And these are the differences.
This is a comparison between conventional acquisition and unconstrained blended seismic data acquisition. So conventional acquisition, we were using a point interval with 50 meters here and here. We have put it to be more denser acquisition. We have 12.5 meters. The main side is a bit big, it's 25 meters by 1.5, and here is 6.25 meters. This is a reprocessed pre-stack depth migration time slice. Reprocessed using conventional acquisition. This is a blended in-field 2017 time slice using our new computer. This conventional acquisition, this blending acquisition. Conventional acquisition, blending acquisition. This is a vintage final pre-stack depth migration from a conventional acquisition with a 30 kilometer subline. This is the same subline. This is the same subline using the new blended acquisition. And this using only 1D phosphate. So, conventional acquisition, fully processed, blended acquisition. This is another example that we blended to final pre-stack depth migration, fully processed. And here is a post-stack time migration image from the blended output. You can see here how the resolution getting better in these horizons at 3 cycles. And even deeper. All technology, conventional acquisition, blended acquisition. Conclusion. High trace density and unconstrained blended data acquisition is a game changer. It's a robust and cost-effective solution. It reduces turnaround with ultra-high productivity acquisition. It gives you access to the best quality ultra-dense onshore seismic data. Argas with CGG provide a unique integrated solution combining blended acquisition, proprietary harmonics-free profile sweep using our clean sweep, accurate measurement of auxiliary data, flawless field operations, advanced QC platform with real-time pre-stack time operation images using dynamics. Reblending was successfully implemented on one of the highest density broadband seismic survey ever acquired onshore and offshore worldwide. We thank Apache and Khalda who allowed us to pioneer this technology in Egypt and for their trust in our innovation and support in pushing back the window. Argas and Argas, CGG Cairo Processing Center. Thank you. Any questions?